All right, guys. I thought to make a quick video on assumed mean because it comes up a lot of years on paper 5 on the ACE test. And it's a problem that it doesn't take you too long if you know the procedure and know what to look for, and the work is really easy to do. But it can be kind of confusing understanding why are we even doing this and understanding the formulas involved. So that's why I'm making this video. And I already recorded this video once, and I'm redoing it because I messed up at the very end. I'm checking my work when I was uploading the video, so I got to redo it. So we're just going to do it. Okay, so why are we doing this? The assumed mean is simply a shortcut, an easier way of finding mean and standard deviation of a data set. The idea is you look at the data values and just YOLO estimate a number you think could be the mean. Now, the ACE problems will do this for you, and often they'll give you the assumed mean. But the idea here is it will make the work easier, something you could do by hand if you didn't have a calculator, even though we do have access to the calculator. The ACE problems can be tricky because they kind of start you off halfway through the process, as we'll see. So here are the key formulas. First, we have this. The mean equals A plus D. This means the real mean equals whatever your assumed mean was plus the average of the differences that the data values are from your assumed mean. So I just want to immediately just jump in and just look at one. Okay. Here's a paper problem where they give you 9 data values. These are times of swimmers. Okay? Check out these numbers. 95, 126, yeah. They say find the values, that's the sum of t minus 120 and the sum of t minus 120 squared. The 120 number, the number in the parentheses that's minus a data value, that is the assumed mean they're giving you. And the idea here is that, look, we can take 120 and it looks pretty close to all of these data values. You could subtract 120 from all of them. You could do this in your head and you could get some small 1 to 2 digit numbers that'd be pretty easy to deal with. And that's why the process is a shortcut. So that's what they ask you to do. Here we can jump to the work I already did on it. So it says find the sum of t minus 120 right here. This is just saying take all these 9 data values and minus 120 from them. 95 minus 120, you get this, negative 125. 126 minus 120, you get 6. So some negative, some positive, 120 minus 120. That's where the 0 comes from. And you do this 9 times. You get these 9 numbers. You just add them up. So that's what the problem asked for. And that's the answer. You'll get the mark from this number. They didn't even ask you to come up with the actual mean of the data set here. But if you have this sum number of 7, all you'd have to do is take the assumed mean of 120 and add the number that you just got 7 from adding up the differences and divide by how many data points there were, 7/9. So I just combined them here as a mixed number, but 120 plus 7/9, that's the actual mean. Okay, jumping back to our first slide, you'll often be asked to find the standard deviation or the variance as well. And the idea of this is that it's almost the same formula that we use on normal mean and standard deviation problems. So here's the formula right here. The square root of the sum of d squared over n, this is the differences, not it's the data values themselves. We can jump to this slide showing the formula for standard deviation compared to the actual formula for standard deviation. So this is d and this is just normal x. And look how similar they are. But rather than x squared, we're doing these differences squared. Why do this? Because d will be a smaller number than x. So it's easier to do. Rather than the mean squared, you just take this average difference and square that. These measures of spread or variance will be the same. And this one will be easier to calculate because the numbers will be smaller. Jumping back to that problem we were just on, we still need to find this sum of the differences squared, and then we need to calculate variance. So all you would have to do is take our 9 numbers we got by subtracting the data values from 120, or 120 from the data values, and just square them all. Square negative 125, square 6, square them all, add them all up, and I got 1,213. Okay? So those are the two answers for part 1. For part 2, find the variance. We're just using this formula right here. They didn't ask for the standard deviation, they asked for the variance, so we don't need to square root it. We can just take all the stuff under the square root. We can take the sum of d squared that we calculated as 1,213 and divide by n 9 data points, so divided by 9. Subtract that from the average difference squared. So the sum of the differences divided by 9, because there's 9 data points, square that. And that's it. 134.2. If you wanted the standard deviations, you would simply take the square root of that number. Now, normally, the problems will start off more like this. Here, let me clean it up for you first, see what it looks like without anything on there. Okay, so here's one. And notice they don't give you any data points. Instead, they do the work for you that they asked you to do in the previous problem that we saw. As in, look, the sum of x minus 50 is 81.4. 50 is their assumed mean, because it's in the parentheses, getting subtracted from the data values. And they already did the sum of the differences for you and the sum of the squares. All they asked for is the variance, and then second part, they asked for the sum of the actual data points squared. So for the variance, we're just doing exactly what we did in the previous problem. Okay? I started off, I found the mean, even though they didn't ask you to do that. I said, might as well. All you'd have to do is take the assumed mean of 50 and add the sum of the differences divided by the data points. They don't show you the data points, but they tell you there's 22 of them. And that's it to get 53.7. So that's the actual mean of this data set. For variance, we're using this formula once again, but not doing the square root of it. And we just take the sum of the squares over n plus this average difference squared. Now, yes, this is where I made the mistake. Hopefully you can already see it, is that the formula tells you to subtract these things. So, allow me to redo this as quick as possible. Yes, and so let's get this incorrect number out of here. And the actual number is 1681. Okay, so there's your variance. And then they ask for the sum of the data values squared. Now, they gave us up here the sum of the differences of the data values in our assumed mean number of 50 squared, but now they're asking for the actual sum of the data values squared. And to do this, we're going to use the fact that, as we said on this slide, that the standard deviation of the actual data set is the same as the standard deviation for the differences that we just calculated, basically, when we did variance. Okay? So what do I mean? Over here, this formula here for the actual data values that's from the ACE formula sheet. All right, let's get rid of all this work. Will be the same as the standard deviation, aka the variance. I'll just do the unsquare rooted version right here. So 16.81, that's what we got in the previous problem for the variance of the data set, and we can set that equal to the formula for variance of the entire data set. And notice what it asks us to do. The sum of x squared, we don't have that. In, we do have that. The sum of the mean squared, I calculated mean to start the problem, although you can tell I forgot to square it. So all I'm going to do is square 53.7 You get 2,883 number, and add that to both sides. Add it to the 16.81, and you get 2,900.5. That's equal to the sum of the square data points times 20 divided by 22. And we can solve this two-step equation by just multiplying both sides times 22. And I get this 63,000 number. And that looks reasonable because the actual data values are bigger than the differences, and this is the sum of all of those numbers squared, so it makes sense that it'd be a bigger number like this. So in summary, when you look at these problems, how do you know it's an assumed mean problem? Well, if you see notation like this and like this, where they give you a sum, x minus the number or x minus the number squared, that's the dead giveaway. It's an assumed mean problem. If they ask for the assumed mean, you just use this simple formula that we see right here, that the actual mean is the assumed mean plus the difference, the average difference, which they probably gave you if you divide by the n. They'll often ask for the variance, and we'll use the fact that we can just tweak our normal formula for variance or standard deviation. Okay, there's assumed mean. Go ahead and try some problems from yourself if you get comfortable with what the heck it even is asking us to do, understanding why we assume the mean. And if you're comfortable with the formulas themselves, then these problems really aren't so tough. All right, good luck studying, guys.